Welcome to Lecture 11 in Multiple Antenna Communications at Linköping University. In this lecture we will consider power control. I will begin by talking about the purpose of power control and different operating points that we can achieve in the capacity or rate region. Then I will talk about the structure of the SINR, or signal to interference and noise ratio. Then we will focus on a particular type of power control, namely max-min fairness, where all the users are getting the same performance thanks to the power control. And I will cover both the uplink and the downlink. And finally, I will provide you a small simulation example where we can see the impact of power control. A large part of this course has been focused on the single cell case, where we talked about the capacity lower bound that we can get for different uses. For example, user K gets log 201 plus the SINR, or signal to interference noise ratio. And there we have an expression that have this particular shape. And we have focused particularly on maximum ratio processing, where we get a numerator that is eta k, which is the power control coefficient that so far have been just a constant, and then we had some kind of factor in front of it, which in the uplink was m, the number of antennas, times rho uplink, which was the transmit power that we have maximally in the uplink, and gamma k, which was the estimation quality. And then we divide by 1 plus something, so this 1 was a noise variance that is normalized, and this something is interference from all of the other users. So we have eta k prime, this is the power control coefficient for user k prime. And then we have a factor in front of that is saying how large is the interference that user can cause. And it contains rho uplink, the maximum transmit power of a user, and beta k prime. So this is a factor telling us how strong the channel from that user is to the base station. And we call this an effective SINR because we are getting a capacity lower bound that is looking very similar to the capacity of a additive white Gaussian noise channel, where we will have this value here as our signal to noise ratio. And therefore it's effectively behaving as if we are having an additive white Gaussian noise channel, but it's actually just a capacity lower bound for a more advanced type of channel where we have multiple users. And therefore this is not the capacity but a lower bound on it. But the interesting thing here is that in terms of the power control coefficients, we have the eta k here, we have the eta k prime here, and then we have some different factors here. And when we derived the capacity lower bound for user k in the downlink, we get the same type of expression. It's just that ak and bkk prime here is different. So in the downlink, with maximum ratio, we were getting AK, which is also equal to M, the number of antennas. We have rho downlink, the transmit power in the downlink, and then we have gamma K, which is still the estimation quality. So it looks very similar, it's just the uplink or downlink power here that is changed. The interference terms looks also similar, but the indices are changed. So we still have rho, but now it's rho downlink, so it's a downlink power, and then we have beta K. So in the downlink, the interference term here is not dependent on the interfering user's channel, but my own channel being user k. So we have beta k here instead of beta k prime. But the important thing is the structure looks very similar in these different cases. And we can consider other types of beamforming methods than maximum ratio processing, and we will still get similar type of expression with different values on A and B. And this holds both in the uplink and in the downlink when we are using a particular type of capacity lower bounds. But the nice thing with maximum ratio processing is that you can actually compute A and B here exactly as a mathematical expression here. There's also another type of processing called zero forcing processing, where you can also compute this once in closed form. And then for other types of processing, you will have to compute them numerically. But the important thing is that since we have a particular shape here, we can actually optimize these SINRs with respect to eta k and eta k prime here for just any numbers of A and B. And then we can apply the result for any type of pre-coding in the downlink and receiver filtering in the uplink. So why is it important to talk about this power control coefficient? Well, if we look at a typical scenario in a practical cell where we have a base station that is elevated at some rooftop, maybe 25 meters above the ground, and then we have users that are more at the street level, and they are at different distances, and there are different aspects in the propagation environment that is changing how strong the signals are going to be when you are receiving them in the uplink or in the downlink. Well, the path loss or large-scale fading coefficient is often very, very small. So a number like minus 65 decibel is actually a pretty large number in this type of setups. So often you are having a much smaller number than that, say minus 97 dB, minus 94 dB, minus 120 dB. You can still operate the system even if you are only receiving 1 billion part or even less of the transmitted energy. It is the nature of the propagation environment and the properties of the hardware that is determining the values of AK and BK. So in particular, the beta values are determined by the channel properties here, but also what type of antennas we're having, what kind of directivity they are having is also something that can be factored into the beta parameters. And then from that we can compute the gamma K, and that will then give us AK. And here we have BK as well. And then of course what kind of hardware we're having in the uplink, for example, is determining what is the maximum power that we are allowed to transmit with. And that could also be based on regulations on how much power a user device is allowed to transmit with. But you can see here we have a 55 decibel difference between these two uses here in terms of their large scale fading coefficient. And that will of course lead to that they can expect very different performance if we are treating them exactly the same in terms of letting them transmit with the same power. But this is where these power control coefficients, eta 1 to eta k, plays an important role. We can compensate at least partially for these differences in large-scale fading between different users by selecting these eta 1 to eta k parameters. So earlier in the course I was talking about this rate region, and we were talking about two different users, say user 1 and user 2. And we can, for user 1, get log 2 or 1 plus and SINR 1, and for user 2 we get log 2 or 1 plus SINR 2. And then there is a region here of different points where the user can get different values at the same time for two different rates of the users. Where we are ending up in this region depends on our selection of these power control coefficients, eta 1 to eta k. So by selecting them in different ways, we can end up inside the region or at different points on the boundary here. And it is at the boundary where we would like to operate the system. And then we are at least operating it efficiently, but then we can trade off between do we like user 1 or user 2 to get the highest rate. And depending on where in the cell these two different users are, the numbers on the axis here can be different. So it might be that user 2 is much closer to the base station, therefore can get much larger number here than what user 1 can get. But we can still compensate partially for that by selecting points that are closer to the maximum value of user 1. So we would like to select eta 1 to eta k so that we are ending up somewhere on the outer boundary. And there are different points there that are explaining different targets of our system. One is to have the maximum sum rate. So this is this point in our case where we have the largest sum of the rate of user 1 and the rate of user 2. Another option is to give the two users the same value. SINR 1 is equal to SINR 2, or we can also say that log 2 or 1 plus SINR is equal to log 2 or 1 plus SINR for the other user. These are of course the same thing because the logarithm and the 1 is not changing the fact that we need the two SINRs to be exactly the same. And then under the assumption that they should be the same, we would like that same value to be as large as possible, and that's when we're ending up here at the outer boundary. This is called a maximum rate because it's the maximum value of the minimum rate in our system. And that is what we will focus on in this lecture. And there are two reasons for that. One is that it's actually one of the main goals of a wireless communication system to be able to deliver the same performance wherever you are. As you're moving around in your network and is getting different values on your beta parameter, then the maximum value that it can achieve here will differ. But you will not notice that when you have a much larger value than you actually need in order to get the wireless service that you're asking for. But you will notice it when all of a sudden your video stops or you cannot get the service that you are asking for. So what is important to users is the worst performance that you are getting in the system. And by raising that worst performance level, we can deliver something that will make the users more satisfied. So that's one reason why we will focus on the max min rate. Another reason is that solving that problem, finding the eta1 to eta k parameter that is delivering the largest minimum rate, is mathematically much more convenient than trying to solve the max sum rate problem. Because the users are interfering with each other, and for that reason we don't have parallel sub-channels where you can allocate power based on this water filling principle, but they're interfering with each other, so therefore we get a much more complicated mathematical problem to deal with, and we won't do that in this course. So delivering the maximum value of the minimum rate is called max-min fairness power control. And it means that we would like to maximize the minimum SINR or the minimum rate in the system, which is the same thing. So every user gets the same performance, even if we are trying to maximize the minimum value, whenever the users are interfering just the slightest amount with each other, which will always happen in reality, one can prove by contradiction that if we are setting a minimum value that we're maximizing, no one will get a larger number than that, because then we can reduce their value just a little bit and improve for everyone else. So when we are maximizing the minimum SINR, everyone will end up with exactly that value in the end. And we have almost the same SINR expressions in the uplink and the downlink, with just different A and B values that were showing up. But we have fundamentally different power constraints, which will lead to different solutions when we are computing this power control. So in the uplink, every user have a maximum power row uplink, and then we are choosing between using no power and full power by varying this parameter eta k for user k. So from 0 up to 1. And we can always select any number in between here, irrespective of what value the others are selecting. So the trade-off rather comes into what SINRs we can achieve at the same time, where we can end up in our rate region. So this is our power constraint. Eta k should lie between 0 and 1 for all of the users. In downlink, it's different because the base station have a maximum power row downlink. And then it needs to allocate it between the different users. And every user should get the value, eta k, a fraction of the total power, which is greater or equal to 0. And then the sum of it should be smaller or equal to 1. And we will actually always use the full power in this lecture. So in the end we will get equal to 1 here. But the interesting thing is how we are allocating the power between the different users. And for consistency we call that power control as well. And mathematically, we can write up the problem like this. We would like to maximize a value that I call SINR bar. This is the value that every user is guaranteed to achieve. And we maximize it by selecting eta1 to eta k, which is our power control coefficients for the k users. And we also maximize with respect to that value. So we would like to make that value as large as possible. And subject to, that means that we have certain constraints that we need to satisfy. And one is that the SINR k, which was the expression I was showing you in the beginning of the lecture, containing A and B and the eta parameters, that one should for every user be greater or equal to this SINR bar value. So for all of users. And then we have the power constraints, which were different in the uplink and the downlink. But apart from that, the structure of the problems are almost the same in both the uplink and in the downlink. However, we get different solutions in the uplink and the downlink because of the SINR expression being different. So we have A and B that are different, and they're also dependent in different ways on the different parameters we're having, and also the power constraints are different. So I will cover the uplink and the downlink separately. I won't show you exactly step by step how to solve this optimization problem, but I will present you with the solution. You can find the derivation in Fundamentals of Massive MIMO book. And then given that solution, I will also explain why it makes sense. So let's start with the uplink maximum fairness case. And we are considering only maximum ratio, but you can generalize this easily by having the A and B terms coming into these expressions. So the SINR looks like this. We have M times row uplink gamma k eta k. And then 1 plus the summation over all the users, row uplink beta k prime eta k prime. And there are a couple of interesting things here. One is that the term here containing the uplink interference is not dependent on which user we are considering. So this number here will be the same for every user. So what differentiates the SINR that different users can achieve is what's going on in the numerator here. So different users will have different values on gamma k. M is the same, rho uplink is the same if every user device have the same maximum power. But gamma k is different, and we can compensate for that difference by letting eta k be different, so that these two values, gamma k times eta k, becomes the same for every user. And as long as they are the same for every user, the entire SINR expression is going to be the same for every user. So what that means in terms of delivering the same SINR for every user is that we should select eta k to be proportional to 1 divided by gamma k. So we put it in here, 1 divided by gamma k, then gamma k times 1 divided by gamma k is cancelling out each other. So whenever eta k is proportional to 1 over gamma k, then we will get the same SINR for everyone. Then, in addition to that, when we have the same SINR for everyone, we also like to make sure that that same number is the largest possible. And how do we achieve that? Well, if we are increasing eta k for all of the users, then we're also increasing the SINR for all of the users. So we would like to make sure that one user is at least using the maximum power, because then we can't increase the power anymore. So we're figuring out who will divide with the smallest number. Well, that is the user k prime, which has the minimum value of gamma k prime, which means that it has the worst channel estimation quality, which in turn means it has the worst beta k value, the smallest one, the one who is furthest away in your cell, or at least have the worst propagation conditions, the smallest large-scale fading coefficient. So in this case, that weakest user in the cell will use full power, and everyone else will cut down on the power according to this formula. And if you insert this back into the expression, this is what you're going to get. Everyone gets a SINR bar value, where we have m times rho uplink still here, and then from this expression, if we put it in here, the gamma k's are cancelling out each other. We have a minimum of the gammas, and I've now divided with it everywhere, so we have 1 divided by that expression here, where we before just had the 1. I've just changed this summation from k prime to k, so that this k prime here won't be confused with this k prime. But apart from that, we have rho uplink, we have a beta term that have the same index as the summation index, and then from this eta we get a divided by gamma, so we have that term here, and then we have this minimum term, and since we divided every term in this SINR expression with the minimum of gamma, then we are moving it here. So this is the SINR that every user in the entire system is going to get when we are applying uplink maximum fairness with maximum ratio processing. And we can use exactly the same type of expressions also when we are having other values on A and B than what we are getting with maximum ratio processing. In that case, we'll have AK here, and then instead of having the minimum of a gamma k divided by gamma k here, we will have a terms here instead. So this is for the uplink. In the downlink, we have something that becomes somewhat different, because now we are not allowing every user to transfer with the full power. We have a downlink setup where we have a maximum power budget, and we will like to divide it between the different users. And when we are using maximum ratio processing, this is the effective SINR that we're getting. M times rho downlink gamma k times eta k, 1 plus rho downlink beta k, and then the summation over all the power control coefficients. And will there be any reason for the base station not to use the full power? No, because if it's not using all the power, well, then it can take what is left and divide it between the different users, and then it can increase the SINR for everyone by essentially increasing the power compared to the noise. And that means that the summation over all of the eta parameters here will always be equal to 1. And what does that mean? Well, if this is a 1, if we can expect that, what will remain is that we have a eta k here multiplied with a factor that is dependent on k. And we would like this factor to be sort of cancelled out by the gamma k, so that it becomes the same thing for everyone. Everyone should have the same SINR. So what we do is that we okay, we look at M here, we don't need to care about that one because it's the same for everyone. So let's remove that one. Then we have rho downlink gamma k divided by 1 plus rho downlink beta k. And then we would like to invert that. So we do that. 1 plus rho downlink beta k, that is what we have here, multiply with a 1. And then we have rho downlink gamma k, that is what comes up here. And then we are essentially done. We just need to make sure that we are actually using the full power. So everyone should get a share, which is proportional to this factor here. And then if we are saying that also the eta k should sum up to 1, well, then we get an additional factor from putting that into an expression. So if we take this eta k and put it back into an expression, we know the summation is a 1, so these two terms will jointly remove these two terms. So we should just get something that is 1 divided by this expression left, and then we have the m. So we get m, and then we have this expression, and we have 1 divided by rho downlink here, so let's multiply with that everywhere. We get rho downlink here, we get rid of this term, we get a rho downlink in front of this summation here. And then once again, I have switched the summation indices from k prime to k here, just to point out that this is the same for every user. So everyone gets this SINR expression for maximum ratio processing. And we can do the same type of methods for other types of processing the maximum ratio. Then we need to play around with the A and B parameter, but we'll still have the same shape that the etas will sum up to 1, and therefore we should remove it. And we have an A and B term here instead, and then we should allocate the power first to make sure that those are canceling out each other. So that everyone gets the same value, and then we should maximize that same value by scaling up the power so we are using the full power in the end. So this is the expression that we're getting. So now I have presented the solution to the maximum power control both in the uplink and the downlink. And let's look more closely on the optimal expressions for the eta k parameters. So in the uplink we get this expression, in the downlink we get this expression. And both of them are containing two different ingredients. One is what we need to do in order to make sure that everyone gets the same SINR, and the other thing is what we need in order to make sure that we are using the maximum possible power. So in the uplink we have the 1 divided by gamma k, that was what we need in order to give everyone the same SINR, and then this here was making sure that we are using the maximum power at one device at least. And in downlink, we had this 1 plus rho downlink beta k divided by rho downlink gamma k. This is what we need in order to make sure that everyone gets the same performance. And then this scaling factor here was making sure that we are using all the power in the downlink. What we can see is that in both of these cases, we are doing the power control as 1 divided by gamma k, and then with some other scaling factors and things. So the power control is inversely proportional to gamma k, except for that we also need to scale it differently in different cases depending on which other uses are in our system. And gamma k had this expression, and gamma k was the estimation quality. And if we have a relatively good signal to noise ratio during our channel estimation, so that tau p rho uplink beta k is here much larger than 1, well, in that case we can neglect this 1 here, and we see that everything is cancelling out except the beta k. So then doing power control inversely proportional to gamma k is approximately the same thing as doing power control inversely proportional to beta k, the large scale freedom coefficient. And in general, this all means that we spend more power on the weakest users than on those that are in the center of the cell. A relevant question now is who is going to perform all of this optimization that I've been describing? Well, in order to compute the power control coefficients, we need to know the channel conditions, so the beta k or gamma k for all of users. We need to know the maximum transmit power, rho uplink, rho downlink. And who could have access to this information? Well, most appropriately, this is going to be implemented at the base station, because every user might know its beta k and gamma k and its rho uplink, but not the other user's information. But they can easily send that information to the base station, and there might be regulations that is telling you what rho uplink is, so the base station already knows that, and when you send uplink signals, the base station can measure beta k and gamma k, for example. So it's easy for the base station to implement these two methods that I was describing in the uplink and the downlink. In the downlink, the base station will just compute the coefficients that it needs and use them. And then that will lead to certain SINRs for different users, which with maximum case was the same. It needs to inform the users of what kind of modulation schemes that are being used in order to achieve that. But that is everything that the users need to know. And then the exact values of the power control coefficients is something that only the base station needs to know. In the uplink, the base station can still compute all of the uplink power control coefficients, and then it tells user K what eta K is going to be, and also what SINR bar we're going to achieve in the cell so that it can adapt the modulation format to that one. So we are actually being able to communicate close to the capacity. And when the users are moving around so that their beta parameters are changing, well, then we need to change the power control. If a user is entering the system, so we have one more user, or if an existing user is exiting the system, so we have one less user, well, in those cases we need to recompute these eta parameters again, and then we apply the same principle once again. So the base station needs to know the downlink coefficients, so they don't need to tell anyone about them, but they need to tell the users what kind of modulation format they're going to use. And if we are in the uplink, then we need to tell the users what power control coefficient to use and what modulation format to use. And importantly, even if everyone gets the same SINR, it doesn't mean that it will be the same all of the time as you're operating the system, because that same value will depend strongly on where the current set of users are. And we will see that in our simulation part. We are considering a simulation example for an urban deployment, but with a single cell to keep it simple, because that is what the lecture has been about, the power control in a single cell. And when it's a circular cell with a radius 500 meters, like this. So in the center we have a base station with 100 antennas, and then the users are uniformly distributed within the entire area. And there are 10 users in the area. And some important properties that we are assuming: we have independent Rayleigh fading channel, so that is what we have been considering in this lecture and many other lectures on massive MIMO. There is no intercell interference. And when it comes to computing the propagation conditions, we have a carrier frequency of 2 GHz, and we have a bandwidth of 20 MHz, which will be important in order to write our results later in megabits per second. So we need to select a large number of parameter values in order to run a simulation like this. For the base station and user terminals antennas, we need to select what kind of antenna gain they are having. And for simplicity, we say that they are 0 dBi, which means that we can essentially neglect the directivity of the handset and of the base station, because they are radiating the power equally in all directions, and they're also receiving power equally strongly in all directions. When we are computing the noise variance, we need to consider the temperature. That is giving us the ideal noise variance, and then you need to add something called a noise figure to that number, because that is describing the noise amplification that is going on inside of the receiver as compared to just the fundamental thermal noise that will exist. We are considering coherence time of 1 millisecond and coherence bandwidth of 200 kilohertz. And if you multiply those numbers together, we have 200 samples per coherence interval to do our communication. Out of those 10 are used for pilots, because we have 10 users. And then we are dividing the rest of it between the uplink and the downlink, so that we have 1/3 or 63 of these samples for uplink, and 2/3 or 127 for the downlink. So from that perspective, we are expecting that we will send more data in the downlink than in the uplink. So let's adapt our operation for that as well. Then we are assuming that the base station is 25 meters above the ground, so it's deployed at an elevated location, and then the users are having a height of 1.5 meters above the ground, which is telling us that there's a height difference of 23.5 meters. And that's important when we are computing the path loss or large-scale fading coefficients. So there are many different models of this, depending on the frequency range, depending on the propagation environment, what type of system we are having. In an urban area, here is the example that I have been using in the simulation. We start by taking the distance between the base station and the user, and it's a distance in 3D, so that's why the height difference is important. Then we are relating that to 1 meter, so we're getting a relative number here. We take the log 10 of that. We multiply it with minus 37.6, so that is a path loss exponent of 3.6 0.76. You should relate that to the powerful exponent of 2 that you have in free space. So we are losing much more energy along the way when we are in an urban environment where we have non-line of sight propagation. And then at the 1 meter distance, we have this parameter here saying that in that case we have a path loss of minus 25.3 decibels. So this whole thing is computed in decibel scale. And then when it comes to the maximum radiated power, this rho downlink, it's 40 watt for the base station, while the maximum radiated power for user terminal, which was rho uplink, is just 0.1 watt or 100 milliwatt. And these are quite typical numbers. And remember that we have 20 megahertz of bandwidth to divide this power over. When we are dropping a user in our cell here, uniformly within this 500 meter radius area, we are getting different signal to noise ratio depending on where the user is ending up. And this is what is shown here. So I'm showing the signal to noise ratio here, and then I'm showing the cumulative distribution function, which is telling us that when we say 0.3 here, we get a certain number here on the curve. In this case, we have minus 10 decibels, and that means that the 30% weakest users in the cell are having a SNR smaller than minus 10 decibels, while the rest of them, 70%, are getting a larger number. So this is the way of showing that type of random distribution. And we can see that we have large variations between users that are in the center of the cell close to the base station, which have an uplink signal to noise ratio here of 20, 30, 40 decibels, while we have the users that are at the edge of the cell, and in those cases we are below minus 10 decibels. And this is just a simple simulation setup where we had a deterministic relationship between the distance and the SNR. In more advanced simulation setups, we usually have some randomness as well, called shadow fading. But in this simulation, this is the methodology that we are using. So we are dropping k users, which are 10 in this case, in the cell, randomly in this area. Then for every user, we are computing the distance and then the beta k followed by the gamma k. Then we are applying our power control, which for maximum fairness is something that I have just described. We do it in the uplink and the downlink to get the eta k parameters. And then based on that one, we are getting the data rates. And when we're using maximum power control, then we have these SINR bar expressions. We put them into log 2 of 1 plus SINR. We multiply with the factor 1 minus tau p divided by tau c in order to get that net spectral efficiency. And then we multiply with the bandwidth and the fraction, 33% of the resources for the uplink or 67% of the resources for the downlink. So let's start with the uplink. Here I am showing you a cumulative distribution function of the uplink data rate in megabits per second that users at different random locations are getting. And there's one curve here for the max-min fairness case. So this is what I've been describing. We are dropping 10 users. We are selecting the power control coefficients for the uplink as I described. And then every user in that drop is getting the same number, the same uplink data rate. And then we are dropping a new set of 10 users. We get a different data rate, and that is giving us these random distributions. So in the worst cases, we are getting this value. In the best cases, we are getting this value here. So even if we in every user drop get the same rate within that drop, we are for different set of the users getting different numbers. So we can say that when we have a larger number here, that is when there were no users very far out in the cell. Well, in this case, we had multiple users being at the edge of the cell. I'm comparing this to the case when we are giving full power to everyone. So everyone is allowed to transmit with the full possible power. Then we get this values here on this blue line. And in this case, in each user drop, we are getting differences in the SINRs between the users, and then we also get differences between different user drops. So that's why we have these variations as well. And we can see some interesting things here. So what maximum fairness is making sure is that the users that have the weakest conditions are getting better performance. And if we look down here, we see that that makes a huge difference. So if we are, for example, looking at what is guaranteed to 90% of the users, well, that is the numbers that are above here. Well, we are getting like 1 megabit per second or so with full power, while we're getting, say, 8 megabits per second in the maximum fairness case. So the data rate that can be guaranteed for 90% of the users is 8 times larger here. And if we go even further down here, what can we guarantee to everyone? Well, there is a huge gap here. So this is what maximum fairness is focusing on. We are letting the users that are close to the base station cut down on the power in order to help the users that are at the edges. And if we compare with the blue curve here, we are getting much worse performance for those that are at the edges of the cell, but there are also users that are very close to the base station, and if they are allowed to transmit with full power, they will get higher rates, up to 40 or more megabits per second, while there is no one who's getting more than, say, 16 or 17 megabits per second in the maximum fairness case. So it's really about taking these large variations in performance that you're getting in your cell if you just let everyone transfer with the same power and squeeze them together to having much smaller variation between different user drops by using maximum fairness power control. And we can also see that from what kind of power control coefficients that we're selecting, the eta case. So here's the random distribution of those ones. With full power, we're always using a 1 here. But with the maximum fairness case, it's only a few users up here. So it's actually 1 user per drop. So that's why it starts at 0.9. That user is using full power. And the rest of them are using less power. And we have this variations here that is describing how the users are distributed over the cells. So down here we have the user in the center, and here we have users close to the edge of the cell. Let's now switch to the downlink. So I'm showing you the cumulative distribution function of the downlink data rate, and we're having maximum fairness and equal power allocation. So in maximum fairness case, we are dropping 10 users randomly. Then we are computing their beta case and the gamma case. We are selecting the power control coefficient at the base station. So we are dividing the power between the users at the base station so that everyone gets the same SINR. And then in another drop of users, we get another set of beta and gamma k parameters, and therefore we get the other SINR that everyone is getting. And those numbers are varying between 31 megabit per second up to, say, 41 or 42 megabit per second here. So these are the random variations depending on how the users are populated in the area. So it's important not only where you are as a user, but also where the other users are at the same time as you. Then we have the equal power allocation curve here, the dashed blue curve, and in that case we are taking the power at the base station and we distribute it equally between the users. Everyone gets the same share irrespective of where they are. And then we are getting larger variations in the downlink data rate. It starts at a smaller number and it ends at a larger number. That means that the users that are at the edge of the cell are getting worse performance, and users that are in the center of the cell are getting better performance. But in general, the variations are much smaller here in the downlink than it was in the uplink. In the uplink, it started with full power transmission all the way down at 0, while here with equal power allocation between the users in the downlink, we are seeing much smaller variations. And we also can observe that if we are looking at the power control coefficients that we're getting. With equal power allocation, we always have the same number here, namely 0.1. Everyone gets 0.1 or 10% of the power because we have 10 users. While with maximum fairness, we have these variations here around actually the same number, but we are sometimes using less power on the users that are in the center of the cell, and sometimes using more power for the users that are at the edge of the cell, but we are not getting any huge variations here. So what is the reasons for that? Well, in the uplink, since the signals are going through your own channels while interference from the other users are going for other channels, we see this large differences that if someone have a better channel than you, they need to cut down on the power to not interfere with you too much. Because if you have a 50 decibel difference in your beta case, then that means that the users that have a much better channel than you will have to cut down on the power by roughly 50 decibels in order to deliver the same received signal quality and therefore a similar amount of interference. But in the downlink, everyone is getting their desired signal and their interfering signal through the same channels. Some users are close to the base station, so they get these signals through a strong channel, and some users at far away locations, they are getting both the signals and the interference through a weaker channel. But we still have that, we cannot say that, okay, one person is going to transmit with 50 decibels more than the other, because then that is going to lead to immense interference for other people. So there you're just compensating more generally for that someone are further away than others, but you cannot create so much more interference to the cell center uses in order to sort of compensate fully to those at the edge of the cells. That will not be a max-min solution. So with that, we are reaching the end of this lecture. We have been talking about that the user performance depends strongly on the transmit powers, and power control must be actively done in order to know what kind of performance you are guaranteeing to your users. And there are many different operating points. What we focused on was the max-min fairness power control, because it's mathematically convenient to work with it, and because it's a good target for design networks, to give everyone the same rate and then maximize that common value. And we showed that in the single cell setup we can get its power control coefficients in closed forms, and we have the simple expressions that we can also understand how they were behaving. We were giving power control inversely proportional to gamma k, which is the estimation quality of user. And some insights that we also get from our simulation is that it's in the uplink that is particularly important to do a good power control, because we have large variations in the signal quality from different users, and we need to compensate for that. In the downlink, we cannot divide the power very unequally between the different users, because that will create immense interference for those that are in the center of the cells. But we still can do better than an equal power allocation and achieve the maximum fairness power control if we are selecting our power control coefficients in the way that we were showing. So that's the end of lecture 11 in multiple antenna communications.